So this unit is really kind of a standalone unit. It isn't really built on much that we have been talking about, but this is all about environmental chemistry. So how chemistry plays into our environment. We are specifically going to talk about the atmosphere and then a little bit about ocean chemistry and things like that. So hopefully this gives you a little bit of a taste in case this was something you were wanting to look into in the future. But we are starting with Earth's atmosphere. So before we get into the chemistry of it, there's a few things that you need to understand about Earth's atmosphere. There are different regions and there's actually a lot of variation between these regions. So first of all, I want to talk about temperature and atmospheric regions, which you can kind of tell by this graph over here. But temperature varies greatly with region. Varies greatly with the regions. If you actually look at this graph, and the way this is set up, it shows pressure and temperature. So we've got temperature on the x-axis, altitude on the y-axis over here, and then pressure on the y-axis over here. So this is kind of how you read it. So temperature-wise, if we want to look at temperature, we're going to look at temperature with regard to altitude. So as we go higher, if you follow the line, the temperature actually goes lower. So that makes sense to us, right? As you go higher and higher, the temperature goes down. But actually, once you get up to the clouds and the temperature starts to heat up a little bit in the stratosphere. So it heats up the higher you go in the stratosphere. And then in the mesosphere, so above your stratosphere, the temperature goes back down again. And then in the ionosphere, it actually goes back up a little. So it's not a continual getting colder, getting colder, getting colder. It actually varies as you go through those different sections of the atmosphere. Now, pressure, on the other hand, does not have a variable like increasing, decreasing. As you go up, pressure is always going to decrease. Okay, so as we're going up, our pressure goes down. It goes to 10 to the negative third, 10 to the negative sixth. The higher you go into the atmosphere, the less particles there are, especially all the way up to where we are going into space. So essentially, less particles means there's less things hitting you, so less pressure. So pressure always decreases with altitude. So let's put that one on here as well. Okay, pressure always decreases with altitude. Okay, temperature varies, pressure always decreases. Okay, so we are going to break these up. We're going to talk about different things that happen in different layers of the atmosphere because different chemical reactions happen in those and they actually affect a lot of what we see. So I'm just going to briefly mention the troposphere. This is where we are. This is where weather occurs. Weather occurs here. Okay, so this is where we get all those clouds. Okay, so troposphere, this is where we are. This is where weather occurs. And yes, there are some chemical reactions we'll talk about in the troposphere. The stratosphere, which is the next one up, that's the one where you might be surprised to find that temperature actually increases. So temp increases with altitude here. And this is really by design. It's so that we don't have so much mixing between all of the layers. Because if you have bad particles in one layer, you don't want them to kind of mix with the other. So if the temperatures are different, they're not going to mix as much. So temperature increases with altitude. This prevents lots of molecule mixing. Prevents molecule mixing. Okay, but since that prevents molecule mixing, it actually means that if you have something bad in the stratosphere, it's probably going to stay there for a long time. And we'll talk about some chemicals that has occurred with as well here in a little bit. So this is kind of like a however, particulate matter here remains for long periods of time. I'm just going to put for a long time. Okay, so if things get into the stratosphere, if they make their way up there, they actually stay there for a long time because you're not going to get much molecule mixing to like break them down or bring them back down to Earth or anything like that. Okay, so we're gonna move on to composition of the atmosphere. So what is in our atmosphere? And you probably know the main two components, of course, nitrogen and oxygen. Nitrogen is about 78.1% of the atmosphere. And oxygen is about 20.9% of the atmosphere, which means that there's not much else, right? That takes up essentially 100%. So the rest of this stuff is really less than 0.1%, less than 0.1% of all of these guys. So there's a little bit of argon, carbon dioxide, of course, neon, helium, methane, krypton, and some hydrogen. Okay, so we've got a lot of those little things. You can see the actual breakdown over here on the right side. But there's a lot going on in the atmosphere, which means there can be a lot of chemistry happening in the atmosphere. So I first want to talk a little bit about nitrogen and oxygen and why there's so much of them. And that's really because they're very stable. But then also, why is there more nitrogen than oxygen? Well, nitrogen is way more stable than oxygen. So it's really hard to break nitrogen down. Okay, so this is extremely stable. Especially because of its triple bond. So triple bonds are way stronger than double or single bonds. Extremely stable, triple bond. Okay, it's actually much shorter. So it's very unreactive. It actually takes a lot of energy to break those bonds. So extremely stable triple bonds, very unreactive. Okay, to actually break that bond, so that triple bond is 941 kilojoules per mole. That's that bond energy, or the amount of energy required to break that bond. It's actually very high. Oxygen, on the other hand, has a double bond, which is still pretty strong, but not as strong as a triple bond. So this is fairly stable, but it is a little bit weaker. So it has a weaker double bond. Okay, so it can be reactive. Okay, and so when I say it's a little bit weaker, instead of 400 or 941 kilojoules per mole, this one is roughly 495 kilojoules per mole. Okay, so it doesn't take as much energy to break the oxygen bond, which is why we see more reactions with oxygen coming up.